module 8 we will learn about Fourier series, Fourier expansions, and we will also step back and talk in general about eigenfunction expansions and the Sturm-Liouville theory. So, Fourier series is one of the most widely used methods in all of engineering and all of science. Okay. We regularly use it in to solve differential equations or to express or to actually simplify problems. One of the most common uses is is when we are studying periodic systems like solids, okay, and if you want to solve Schrodinger equation for solids, then we expand them in periodic functions, and this is where we use Fourier series. So, what I am going to do in this module is talk about Fourier series just as though I mean we will just talk about Fourier series as it is, and then we will step back and try to go back towards the general method of eigenfunction expansions and the theory of eigenfunctions expansion, which is the Sturm-Liouville theory. The advantage of understanding the Sturm-Liouville theory is that you can do for several different functions. You do not need to only use Fourier's series, you can use other series also. So, let us get started. So, in the first lecture I will be talking about Fourier series and Fourier expansions. So, now before I talk about Fourier series or Fourier expansions, the one thing that you have seen very often is I mean this from linear algebra. If you have a vector v that belongs to some vector space V, capital V, okay, then we know that we can write V as sum over n equal to I should write 1 to b, and I will write it as C n, where b 1, b 2 up to b b are basis vectors, are b basis vectors, and C 1, C 2 up to C b are coefficients. So, what I have said is that you can take any vector and expand it as a linear combination of basis vectors, okay, and there are b basis vectors. So, this is in a b dimensional vector space. Okay. So, this is something that you are fairly familiar with, you have seen this quite often. Okay. Now, we also said that recall from your linear algebra that the space of functions is an infinite dimensional vector space. Okay. So, the dimensionality is infinite, and so if you try to do something like this, okay, so suppose you have, so we might be able to think of something like this, f of x is equal to sum over n equal to 1 to infinity, there are infinitely many, and you have C n and you have B n, this is a basis, n of x is basis vector, and now this is a vector space of function. So, we will call it a basis function, and there are infinitely many of them. So, you have this series goes all the way to infinity. Okay. So, this is in general you can think of this as basis function expansion. What it says is that you can take any function and expand it as a linear combination of basis functions. Okay. Now, why is this helpful? I mean this is particularly useful if the basis function has some simple form. Okay. So, particularly useful if basis function has some simple form. Okay. Now, this is the motivation for introducing the Fourier series. Okay. So what we are going to do is Fourier series. When we talk about Fourier series, we are thinking about basis function expansions, and what we want to do is to do this basis function expansion. Now, in general, you do not know what your basis is. If you have infinitely many, if you have the space of all functions, okay, then your basis set will be infinite. There will be infinitely many basis functions. Okay. So are there cases when this can become simpler? Okay, and the answer is yes. Okay. So we will look at the Fourier series. Okay. Now, consider functions that are periodic with period 2L such that f of x is equal to f of x plus 2L. Okay. So this is a periodic function, the period is 2L, okay, and what I am going to do is I am going to, so what does a periodic function look like? So if you were to plot this function, and I will deliberately show it as a slightly longer in the x direction. So, this is 0, this is 2L, let me make L, 2L, 3L, 4L, and then I have on the minus side I have minus L, minus 2L. Okay. So now what I can do is I can just let us say I have a function that looks like this. Now, since it is periodic, then the value of the function here and here should be the same, and then it has to again do exactly the same thing. I am just exaggerating all these wiggles just to show what a periodic function will look like. So on, and then similarly on the other side too. So okay. So this is what your periodic function will look like. So basically you take the value of the function at any point, okay, it will be the same. If you shift by 2L, you will get to exactly the same value. Similarly, you shift by 2L on this side, you will get to exactly the same value. You can keep going, you go by 2L, oh sorry, you go by 2L, you go by 4L, etc. You will basically get the same value. So the function just keeps repeating itself. One of the things about this function is that you can take any point, you can take this point and you go to 2L ahead and you will end up with exactly the same point. If you go 2L forward or you go 2L backward, you will end up with exactly the same value. Okay, so the value of the function will be exactly the same. Okay. So these periodic functions, okay, they actually they appear very naturally in lot of very natural way to study let us say macroscopic systems in statistical mechanics. This is one point that will become clear when you do your statistical mechanics courses, that you treat the system as periodic. Okay. But anyway, this is just one point, but also they, as I said more they might appear in theory of crystalline solids. So a crystalline solid is periodic in space. Okay. So the same pattern keeps repeating. So in that you use periodic functions, but it is much more general than that. That is what I want to emphasize. Now, suppose I consider a periodic function, then I can do the same expansion f of x is equal to sum over n equal to 1 to infinity, and I can use Bn or Cn Bn of x. What I will choose, okay, so since we have the periodic condition for x, okay, so one way to ensure that f of x is periodic is to choose Bn of x equal to Bn of x plus L, x plus 2L. Okay. So the idea is your basis functions are also periodic with the same period 2L. Okay. So now what that means is, if the basis functions are periodic, then any linear combination will be periodic, any linear combination of basis functions will be periodic with the same period 2L. Okay. So now what is the choice for basis? Okay. So suppose you choose, suppose we choose Pn of x is equal to sin n pi x cosine n pi x by L. Now notice that both these are periodic functions. So sin n pi x by L is equal to sin, or I will put little l here, is equal to sin n pi x plus 2L by L. Okay, you can verify this, okay. So this right hand side I can write as sin n pi x by L plus, now sin 2n pi plus sin n pi x by L, this is nothing but sin n pi x by L. Okay. So clearly this is similarly, so sin n pi x by L is periodic with period 2 pi, with period 2L. Similarly cosine of n pi x is also periodic with period 2L. Okay. So this is the first thing, that both sine and cosine are periodic with period 2L. Okay. So this particular choice where you took it as sin n pi x by L, so you can take any value of L n. Okay. So this is true for any integer n. Okay. Integer means n can be 0, plus minus 1, plus minus 2, and so on. Okay. Now so now with this we can either choose sine or cosine. Okay. But we notice one thing, we notice that sine of n pi x by L is equal to minus sine n pi minus x by L. Okay. So sine is an odd function. Okay. So any linear combination of odd functions. Okay. So suppose you take a linear combination like this where Bn is odd. Okay. Then you will get an odd function. Okay. Similarly cosine is equal to plus cosine of n pi minus x by L, this is an even function. So what that means is, suppose you just do an expansion where Bn is cosine, then f will be even function. Even function means it has to have the same sign on both sides. Okay. So odd function means it has to have opposite sign on both sides. Okay. Now if you look at this function, okay, it is neither even nor odd. So f of x equal to minus f of minus x and f of x equal to f of minus x, that is an even function. So now this motivates us. So for a general f of x that is neither even nor odd, we choose or we define Fourier series as, okay, Now also notice that this, if n equal to 0, the sine term vanishes, sine term goes to 0. If n equal to 0, the cosine term goes to 1. Okay. So what is defined as is the following way. Let me write this in a different color. So f of x is equal to a 0 by 2 plus sum over n equal to 1 to infinity a n cosine of n pi x by L plus b n sine of n pi x by L, where a n and b n. Okay, now a 0 and a 1, a 2, it goes all the way to infinity, are called the cosine coefficients. These are scalars. Okay, and b 1, b 2 up to infinity are called the sine coefficients. Notice that b 0, there is nothing called b 0, okay, because if n equal to 0, there is no sine term. Okay. So this is called this is the definition of the Fourier expansion or Fourier series, or it is called, or you use the term Fourier expansion of f of x. Okay. So you are expanding the function in a Fourier series. So you are writing this function as a linear combination of cosines and sines. Okay. There is a constant term. Okay. So now any periodic function. So the important thing is any periodic function. Okay, these two words are important. You can take any function and it can be, but it has to be periodic. Any periodic function can be expressed as a Fourier series. Okay. Now when I say it can be expressed as a Fourier series, what do I mean it can be expressed? So what I mean is that this is convergent. That means the you take more terms, you get closer to the actual function. Okay. Now the other thing is when I say any, it f of x can be discontinuous. Okay. F of x can be discontinuous also. Okay. It need not be continuous. Okay. Now a few more things I want to mention about Fourier series. Okay, is the following. Now let us get back to our vector. So when we write b is equal to sum over n equal to 1 to b c n b n, okay, then these are basis functions. So suppose I do b j dot v. Okay. So if I dot the vector with one of the bases, okay, then this will be I can write it as sum over n equal to 1 to b c n b n dot b j. Okay. And usually the basis functions are orthogonal. So b n dot b j equal to 0 if n is not equal to j. Okay. So and is equal to b j square if n equal to j. Okay. And this can be chosen to be 1. Okay. So can be set to 1 Okay. So, if you make bj unit vectors, then you can set the length of bj equal to 1. So, bj dot v is nothing but it will just give you cj. Okay. So, what you can do is you can write cj as bj dot v. So, the coefficients of this basis expansion, okay, can be got by taking a dot product of the vector with the basis vector. Now, the same thing can be done, okay, you can do a very analogous thing for functions. Okay. So, if you have your Fourier series f of x equal to a 0 by 2 plus sum over n equal to 1 to infinity a n cos n pi x by L plus b n sin n pi x by L. So, if you have something like this, okay, then I mean I should emphasize that this factor of 2 is just for convenience. Okay, you do not need to take this, but this is done by convention. Okay, so, this is just a convention and we will see why it is convention, okay, but it is useful for it is done for a particular reason. So, I can write a n is equal to, okay. Now, I have to take a dot product of this function with this basis. Okay. So, or let me write a j is equal to, so I will take now in this case the dot product. So, I have cos j pi x by L. Okay, now, I have to take a dot product with f of x. Okay. Now, in the space of functions, a dot product is typically defined in this way, and what is done is that this has a factor of 1 by L. Okay, this is taken in front. Okay. So, this turns out to be a very useful way to define aj. In fact, you can easily verify that something like this is true, okay, by taking various choices of f of x. Okay. Now again this 1 by L factor is done actually to it is like this normalization constant. It is like that is what sets bj square to. So, this is aj and this is valid for j equal to 0, 1, 2 up to infinity, and bj you can write in very similar way. You can just write it as 1 by L minus L to L sine of j pi x by L f of x dx. Now, j equal to now sin x, the 0 term does not exist. Okay. So, you have j equal to 1, 2, 3, so on. Okay. So, this is the definition of the Fourier series. Okay. So, this is what is meant by the Fourier series, okay. Fourier series or Fourier expansion. Okay. And as I said, you can do this for any function, can do for both continuous and discontinuous functions. Okay. Slash discontinuous functions. The other important thing, okay, and let me emphasize this point, okay, can write unknown function as Fourier series. This is probably the most important application of Fourier series. So, you write an unknown function as a Fourier series, okay, and what this does, what happens when you write your unknown function as a Fourier series. So, you had f of x is equal to your, so if this is an unknown function, now when you write it as a 0 plus sum over n equal to 1 to infinity a n cosine of n pi x by L plus b n sin n pi x by L. Okay. On the right hand side, the unknowns scalars a 1 or a 0, a 1, b 1, b 2 and so on. Okay. So, the unknowns so now instead of having an unknown function, you just have unknown scalars. Okay. And this is a this turns out to be a very powerful way to solve, very powerful method to solve for f of x. Okay. So, now instead of having a function as an unknown, okay, what you have is all these scalars as unknowns, and then what you will get is you will see that we will see how this can be used to solve differential equations. Okay. So, this is extremely useful in solving differential equations, both analytically and numerically. Okay. So, I should emphasize that that numerical solutions are also very okay. So, especially when you are doing especially when you are solving these equations numerically, okay, this expansion is very useful. So, I will conclude this lecture here. Okay. So, in the next lecture we will actually look at some ways in which Fourier expansion is used. Okay. We will see we will look at Fourier series of some simple functions, and then we will also see how you apply it to solve differential equations and how it transforms the problem of solving differential equations. Thank you.